Transcendental functions are as important as algebraic functions. We will devote this video to look into the limits of some transcendental functions, namely trigonometric, exponential, and logarithmic functions. Just like in the previous video lesson, we will solve and illustrate the limit of these functions using table of values and graphs. Before we can proceed, it is important to note that to properly graph these functions, using graphing application or calculator is highly recommended. We will define first what is exponential function. Let b greater than 0 such that b is not equal to 1. The exponential function with base b is defined by f of x equals b power x, where x is an element of real number. The function f of x equals 2 power x is an example of exponential function because it satisfies all the conditions of an exponential function. For our base, this is greater than 0 and our base is not equal to 1, and the x is the exponent of our base 2. In evaluating the value of the function, just simply substitute the value of the x in our original function. For instance, if x is equal to 0, then 2 power 0 is equal to 1. If x is positive 1, then 2 power 1 is equal to positive 2, and so on. Recall in your Gen Math that the logarithmic function is the inverse of the exponential function. We define the basic logarithmic function as follows. Let b greater than 0 such that b is not equal to 1. The logarithm of x to the base b is defined by f of x log x to the base b, where x is an element of an open interval 0 until positive infinity. In the function f of x equals 2 power x, the value of the function at x equals 2 is positive 4. This 2 is the base, this is the exponent, and 4 is the value of the function. Its logarithm form is like this. The logarithm of 4 to the base 2 is 2. This 4 represents the value of the function x. This is our base, this one. And our 2, the answer of the logarithm, is the exponent in our exponential function, which is this one. For f of 4 equals 16, the logarithm form of this equation is log 16 to the base 2 is 4. If b is not specified by any number, like the 3 expression on the right, such logarithm is called common logarithm, which has base equal to 10. With that, log 100 is 2 because the base here is 10 and 10 power 2 is 100. For log 1000, that is 3 because 10 power 3 is 1000. And lastly, for log 1, that is equal to 0 because 10 raised to the 0 power is 1. If the value of b is equal to e, which is referred to as the Euler's number, the function defined by f of x equals e power x is called the natural exponential function. Its inverse, which is the natural logarithmic function, is defined by f of x equals ln x. And this f of x equals ln x is equal to f of x equals log x to the base e. This constant e is approximately equal to 2.72. For example, if x is equal to positive 2, then e power 2 is approximately equal to 7.3891. And for its inverse, the natural logarithm of 7.3891 or the log 7.3891 to the base e is approximately equal to positive 2. We are now going to evaluate the limit of e power x as x approaches 0 using the table of values and its graph. We assign values from the left of 0, and for x equals negative 0.5, by substitution, that is approximately equal to 0.6065. In calculator, just follow this syntax. On the right is the table of values for our x from the left of 0. We will now assign values of x from the right of 0. For x equals positive 1, e power 1 is approximately equal to 2.7183, and this is the syntax in calculator. And the table of values from the right of 0 is shown on the right. Since both the left and the right side of x have the same value, which is approaching to 1, then we conclude that the limit of e power x as x approaches 0 is equal to 1. The graph of this function is found on the right. This time, we are going to evaluate the limit of the natural logarithm of x as x approaches positive 1. For x equals 0.1 from the left of 1, ln 0.1 is approximately equal to negative 2.3026. The complete table of values from the left of 1 is shown on the right. And from the right of 1, for x equals 2, the value of our ln2 is approximately equal to 0.6931. The complete table of values from the right of 1 is shown on the right. From this result, we conclude that the limit of ln x as x approaches 1 is 0. We will now evaluate the limit of log x as x approaches 1. From the left of 1, for x equals 0.1, log 0.1 is negative 1. These are the values of the function from the left of 1. Let's proceed now to the value of the function from the right of 1 and its graph. Therefore, based on the table above and its graph, the limit of log x as x approaches positive 1 is 0. Let us now proceed to the limit of trigonometric function. Recall the different trigonometric function, the Sokoto-Wachusha-Kau, and their respective graphs presented and discussed in pre-calculus. Before anything else, we need to set first the mode into radian. If this is your calculator, just click the dig for the degree until it is changed to rad for radian. To evaluate the limit of sin x as x approaches 0, we will assign values of x from the left and from the right of 0. For x equals negative 1, sin negative 1 is approximately equal to negative 0.8415. In calculator, just press sin, then the negative and 1. Before using calculator in this part, you need to make sure that the mode is already in radian. Use the same process for the values of x from the right of 0. This is the complete table of values for this function and its graph. According to the table of values, the limit of sin of x as x approaches 0 is 0. And from those data, we can deduce the following limit of sin x for some values of x. For example, for limit of sin x as x approaches pi over 2, in calculator, just press sin pi divided by 2 and the result is positive 1. Before we can proceed to the limit of some indeterminate forms, let us first consider when can we have an expression of 0, undefined, and indeterminate. For 0 divided by 1, the answer is 0 because 0 times 1 is 0. So this is an example of a 0 expression. For 1 divided by 0, this is an undefined expression because we cannot find a certain number multiplied to 0, the product is 1. How about 0 divided by 0? we can have an answer of 1 because 1 times 0 is 0. But we can still have 2 because 2 times 0 is 0. And we can also have 3 because 3 times 0 is 0. In other words, we can have lots of number here. That means to say, we cannot identify a certain number as an answer of this expression. This kind of form is what we called as indeterminate. For this expression, sin t over t, this sin t over t when t is 0 is indeterminate. But we can still solve for the limit of sin t over t as t approaches 0 by using the table of values and its graph. By substituting t equals -1, sin t over t is approximately equal to 0.8415. In calculator, just use that syntax. On the right is the complete table of values and the graph of sin t over t. And according to them, the limit of sin t over t as t approaches 0 is 1. Another indeterminate form, we will evaluate the limit of 1 minus cos t over t as t approaches 0. These are the values of the function from the left of 0. And the values of the function from the right of 0 are the following. Based on this table, we can conclude that the limit of 1 minus cos t over t as t approaches 0 is 0. And for this function, e power t minus 1 over t as t approaches 0. So for t equals -1, that is approximately equal to 0.6321. And on the right is the complete table of values from the left of 0. This is the table of values from the right of 0. By comparing the graph and the table of values of this function, we can conclude that the limit of e power t minus 1 over t as t approaches 0 is +1.